Welcome to today's paper reading. Today's paper is titled, NExT, Teaching Large Language Models to Reason About Code Execution. This paper was published on the AR14 preprint by Ansong NI and colleagues from Google DeepMind. The NExT method is designed to teach large language models, LLMs, to understand and reason about the execution of code. This is achieved by having the models inspect execution traces and reason about the runtime behavior of programs using chain-of-thought rationales. The method employs self-training to create a synthetic training set of execution-aware rationales that lead to correct solutions for tasks such as program repair, without the need for manual annotation. Experimental results show significant improvements in the fix rate of a Palm 2 model, with an absolute increase of 26.1% on the MBPP dataset and 14.3% on human eval. Additionally, the quality of the rationales has been improved, as verified by both automated metrics and human raters. The model also demonstrates the ability to generalize to scenarios where program traces are not available at test time. The introduction of this paper highlights the growing capabilities of large language models, LLMs, in assisting with various coding tasks. However, these models still face challenges when dealing with more complex software engineering tasks that require reasoning about program execution. The authors emphasize the importance of providing explanations alongside code solutions to help developers better understand and make informed decisions. Drawing inspiration from human debugging practices, the paper introduces naturalized execution tuning, NExT, a method aimed at improving LLM's ability to reason about program execution using natural language and execution traces. This approach not only enhances interpretability but also increases the diversity of solutions predicted by the model. Figure 1 illustrates the NExT approach, which involves fine-tuning a large language model, LLM, to incorporate execution traces into chain-of-thought rationales for solving coding tasks. The process includes iterative self-training from weak supervision, where the model learns from samples that lead to correct task solutions. This method aims to improve the LLM's ability to reason about program execution by leveraging natural language rationales that are grounded in the execution information of the program. Table 1 presents the few-shot prompting repair accuracy using greedy decoding across various models and prompting methods. The results highlight the effectiveness of different strategies, with some methods showing significant improvements over others. Notably, results that are worse than the previous row are underlined in red, providing a clear visual indicator of performance degradation. The NExT algorithm is built upon existing self-trained reasoning approaches, employing expert iteration to enhance a base large language model, LLM, using synthetic rationales sampled from the model. For each iteration, rationales and code solutions are sampled in tandem from the current model. Initially, few-shot prompting is used, transitioning to zero-shot prompting with trained models and subsequent iterations. The algorithm focuses on sampling solutions from challenging problems, significantly reducing sampling costs and improving repair accuracy. After sampling, candidate solutions are filtered using unit test execution results to identify plausible rationales leading to correct fixes. The model is then fine-tuned from its initial checkpoint to maximize the probability of generating target rationales and code fixes, avoiding overfitting to lower quality instances from early iterations. In this section, we discuss the experimental setup and results. The base model used for evaluation is Palm 2L, a large language model. The datasets include MBPPR, a new repair benchmark created from MBPP, and HeFix Plus, an augmented version of human evalfix. The evaluation metrics include pass at K, which measures the fraction of solved repair tasks using K samples, and a proxy-based evaluation metric for rationale quality. The main results show that NExT significantly improves the end-to-end program repair performance of Palm 2L, with notable gains in both fix rate and rationale quality. Additionally, the model demonstrates strong generalization capabilities to the HeFix Plus benchmark without additional fine-tuning. Figure 3 presents the greedy decoding results on the MBPPR dataset for the Palm 2L Plus NExT model and various existing large language models, LLMs. The data clearly shows that Palm 2L Plus NExT achieves superior performance compared to other strong LLMs. Specifically, it records a significant 29.4% improvement in end-to-end pass-at-1 and an 11.1% enhancement in proxy-based pass-at-1 metrics. These results underscore the effectiveness of the PaLM-2L plus NExT model in program repair tasks, demonstrating its competitive edge in reasoning with execution. Table 2 presents the improvements achieved by NExT on the PaLM-2L model when applied to the MBPPR dataset. The data shows a significant 26.1% absolute improvement in the pass-at-1 metric, indicating that NExT enhances the model's ability to correctly fix programs. Additionally, the gains in pass-at-K metrics are generally higher for smaller values of K, suggesting increased confidence and diversity in program fixes. For comparison, results from GPT 3.5 and GPT 4 are also provided, highlighting that PaLM-2L with NExT outperforms GPT 3.5 across all pass-at-K metrics. Figure 4 presents an analysis of the effects of removing rationales and/or traces during the iterative training process of NExT. The figure highlights the performance of the model with respect to different training iterations, showing the impact of these ablations. It uses consistent grid line intervals on the y-axis to facilitate easier comparison among different curves, despite varying min/max values for clarity. This analysis is crucial for understanding the role of rationales and traces in the model's performance and generalization capabilities. Table 3 highlights the performance of PaLM-2L plus NExT when trained with traces and tested without them. The model demonstrates a significant improvement over PaLM-2L, achieving an end-to-end fix rate of 40.8%, which is a 21.8% enhancement. The proxy-based evaluation results are also consistent with this improvement, indicating the effectiveness of the model's reasoning capabilities even in the absence of traces. Table 4 presents the generalization results of PaLM-2L plus NExT models on the HeFix Plus dataset. These models were exclusively trained with the MBPPR dataset. The table highlights the performance differences when execution traces are provided versus when they are not. It also examines the effect of including or excluding rationales in the model's reasoning process. The results indicate that the inclusion of traces significantly improves the model's ability to generalize to out-of-distribution repair tasks, as evidenced by the higher pass-at-1 rates. Additionally, the table shows that PaLM-2L plus NExT models perform competitively even without traces, demonstrating their robustness and adaptability. Table 5 presents the results of human annotation on the quality of rationale explanations generated by 3 models, PaLM-2L plus NExT, PaLM-2L, and GPT 3.5. The evaluation is based on ratings from 104 sampled MBPPR repair tasks, focusing on 2 main aspects: the helpfulness of the rationale in explaining bugs and its correctness. This intrinsic evaluation provides insights into the effectiveness of the model's rationales and understanding in addressing software bugs. In the realm of program execution reasoning, previous research has focused on leveraging the execution states of partially generated programs or training neural networks to mimic program execution. Our work, however, concentrates on teaching large language models to reason about program execution using natural language. Regarding program repair, several studies have utilized execution information such as traces or test diagnostics. Unlike these approaches, our method, NExT, inlines indexed variable states as code comments for efficiency. Lastly, in supervised chain-of-thought reasoning, LLMs have been shown to solve problems more accurately when guided step by step. Our approach differs by using self-training to generate high-quality rationales with minimal manual annotation. In this paper, the authors introduce NExT, a self-training method designed to fine-tune large language models, LLMs, for reasoning with program execution using traces. They demonstrate that the PaLM-2L model, when trained with NExT, produces high-quality natural language rationales and achieves improved success rates on 2 specific program repair tasks. Looking ahead, the authors plan to extend the application of NExT to a wider array of program understanding tasks and to expand the trace representation to accommodate more programming languages. Thank you for watching.